Okay, so assuming everything's working, the speaker is picking up, and yeah, we are going to continue our multi-step graph sketching. I want to call it an algorithm. Okay, it's going to be a step-by-step instruction, where if you follow it, you'll have a really good clue of what the graph would look like. And not only that, you will be able to add something today that is, as I said yesterday, testing the limit. So first off, I'm going to see how well we do. I did all this for you, but I think I'm actually going to do it again just to get everyone back on track. Okay. Take a look to see if your homework, the one question I asked you to try to reproduce yesterday, follows these answers and get this graph at the end. Once we get this hammered down, I want to show you something new today by testing the limit, and what that means is checking the behavior near vertical asymptotes and checking the behavior at the end of your graphs. And that will give you a better clue of what the graph looks like. That's important for today. Okay, so take a look. While some of you are checking, everyone else, hands up, who did get a chance to try example 2, this function on your own yesterday? And there's no real point. How about we go through it together? Yeah, and for sake of people who were away yesterday too, that might be a better, for you. So then, if that's the case, I am going to open a fresh, same copy but fresh. Okay. So I am going to do the second example together. And we will do the third example together in hopes that people will understand what we're doing. And then I will show you what it means to test the limits. While we are here, allow me to open this and turn it into a PDF while everyone's getting ready. What you will need is a sheet from yesterday. So that we'll, let's see. That's not a good sign. Oh, it's just me, or it's taking a really long time. I'm gonna have to timestamp this so that everyone knows where the class starts. And all right, let's do it. Starting fresh. So just to recap from yesterday, from now on, we are going to be looking graphs that are not just polynomials, but in this case, introduction, a reciprocal. That means the denominator has a really good chance of being a 0, or we have to watch out for that. So the best way to start graphing from this point on, if you see a reciprocal, is to follow a set of instructions using the acronym DISAI, D-I-S-A-I-M-I-C. Each teacher might have a different acronym for you. The last 3 here are going to be more focused in through calculus. And so, oops. Oh, and I think I made a mistake. This shouldn't be intervals. It should be inflection point, but I'll correct myself once we get into calculus, so don't worry too much. Let's go through it. We have 1 over 2x minus 3, and each of these, as we go through, will give you a small picture of our graph. We piece all these information points together and it will create a beautiful picture. All right, so starting off, if you did the homework, your domain, well, X could be anything. But remember, at the same time, we know that we can't have the denominator equal a 0. So if it did equal a 0, 2x would equal a 3, and that means x would equal 3/2. Right? So that means in this case, we have a restriction on the domain where x cannot be 3/2. Making sure I'm sharing the right. Okay, so there is my domain. Next step, intercepts. Intercepts are really helpful. Let's start with the y-axis. Oh, sorry, the y-intercept, which means the x value equals a 0. Following, you plug in your 0. This becomes 0 minus 3. My x-intercept, sorry, my y-intercept is -1/3, which means I have a point 0, -1/3. Okay. For the x-intercepts, that means that my y value is a 0. So when will this fraction ever equal a 0? As of right now, the answer is always never. Okay, that will never be a 0. Therefore, no x-intercept. Never will happen. So we're done D, we're done I. Hey, pardon? This is from yesterday. I think it was the one that I gave you for homework. So I did this one together. This one's the next example. Okay. But it seemed that a lot of people didn't get a chance to do it, so we're going through it. Today's going to be a longer lesson because of this, I think. Or if you get the hang of it, there's more homework. Here we go. Symmetry, I said skip for now. It's helpful, but it's not perfect, right? It's a helpful secondary confirmation tool, but for now we'll just skip. So S, I'm going to skip. A, asymptotes. So today, as I said before, we're going to use a bit of common sense and logic to argue our vertical and horizontal asymptotes. But today we will learn why that makes sense and how we know where they are without too much logic in the future. Vertical asymptote, we automatically can look at our domain and our restriction. Our vertical asymptote is automatically at 3/2. The horizontal asymptote, there's actually a way to find this by calculating. But for today, I'd like you to use your logic and say, hey, what is the one number that this function will never be? So what is the one number the y value will never be? 0. So for now, would you please write 0? And I will show you how we can test the limit and figure that out mathematically. Okay, so put a little star next to it, horizontal asymptote. And lastly, intervals. This is going to be a big hint. You're using a sign chart. Be with me. This is for you. And in the sign chart, as a reminder, on the top, you are putting all x-intercepts and all vertical asymptotes in there. There are no x-intercepts, so I'm good. But there is a vertical asymptote, so I'm putting that there. On the left side, again, any part of the function, especially if it can change signs, are going to be placed on the left column. So a 1, no matter what the x value is, it will be a positive. But for here, left of 3/2, so left of 1.5, let's throw in -1 million. -1 million times 2 minus a 3, yeah, that's going to be a negative value. Or above 1.5, let's do a positive 1 million. Positive 1 million times 2 minus 3, that's like a drop in the bucket, right? it's going to be a positive. So my function is going to be positive. And as a reminder to myself, at 3.2, there is a vertical asymptote. So I'm going to piece all of this together. Using this information, should be able to graph. I have a vertical asymptote at 3.2. I have a horizontal asymptote at y equals 0. I have a y-intercept at negative 1 over 3. So I'm going to do around here. That's a negative 1 over 3. Do you have any other information? No. So you're thinking, how do I graph this? Right now, the only step you have that I've given you really is the sign chart. Today, you're going to have one more clue to make sure you're doing this right. Okay? Based on the sign chart, if I am looking at the left side of this vertical asymptote, it has to be negative. It has to be underneath the x-axis. I also know I have to go through negative 1 over 3. I also know it can't go through this dotted line. Using logic, you would say, yeah, it's probably going to do that. And then after the vertical asymptote, it suddenly becomes positive. So it's going to teleport and come down this way. Does it go through? No, there are no other x-intercepts. So I know it won't go through the x-axis. So again, once again, using logic, it's going to be something like this. There's your graph. So I'm going to challenge you to try this. It's the same steps. And by the final answer, since this is a video, I'm just going to do this for you right now. It's going to look, let's see, it's a 5 negative from there. It's gonna, I believe it's going to look something like that with a y-intercept of 4 over 5. Okay, that's the final sketch. See if you can get this going through the steps. Just put a little sketch on it for yourself. And while we're here, while we're waiting, how many people are here? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Don't know if I have enough. 4, 7, 10, 14, 16. Oh, 17. If anyone doesn't want one of these, be a good Samaritan, I guess, and let the other people have it. So as a reward for being here and not making my life hard, I have a gift for you. Normally what I do for my grade 12s, because there's clearly so much graphing involved, I get everyone one of these. It's a Post-it note, but it has a graph on it. It's about $1 a piece. So every year if I have 2 grade 12 classes, it's about $60 on my part. I think it's helpful, but clearly because we're graphing so much, the end goal is that you're able to freehand it at any point in time. I want you to be able to freehand your x-axis and your y-axis and your dotted lines and whatever, so you can sketch it at any point, no matter what kind of paper you have. But until then, if you need a helping hand to make sure you're doing correctly, you may use this. So is there anyone here who does not need one? Who does not? Oh, perfect. And everyone else, thank you, Evan, for being good to me. I'm going to ask you just hold on to this. If you don't need it, that's fine. But anytime you have sheets like that and you have to end up graphing it, if you want to try to do something neat, then well, yeah, you have that too. Okay, Alex, catch. Catch. 4, 5, 6. Grab one and go. 3, 4, and 4.
I don't even need that.
Okay, perfect. There's 1, 2, and 3. Pass it down. And 1, 2, 3. Okay. Quick instructions how to use this. Every part of this Post-it note is glued except for the top rim, right in the middle. So just pull on that. and you can peel it off, and you'll see blue on the two edges. You stick it on any paper you want, and see if you can sketch it. Okay, so that's going to be your answer. See if you can get to this, and if you need help instead of drawing in freehand because your straight lines suck right now, use this. With me? So far so good? All right, so there is your answer. The reason why I feel like I'm rushing a little bit is because I want to show you how we can do this without using logic, how we can actually calculate your horizontal asymptote, and also how can we confirm that it teleports like this, like it goes from down, or it goes from the negative direction and comes from the positive direction. Okay, this is what it means to test the limit. And if I had time again, I would have done a minds on with you to understand it. But here is a new notation. So if you have some space on this sheet, like I do, like I'm going to use up all of this, then add it with me here. If you do not, you may want to write it on a separate piece of paper. From now on, every time we do the vertical asymptote and the horizontal asymptote, you will be performing this to confirm. Instead of guessing where this is going, testing the limit will tell you that I must be coming from here and I must be leaving down here. I must be finishing off here and I must be starting here. Like it will confirm that for you. The vertical asymptote, for example, here, let's test the limit for the vertical asymptote. We've established that the x is going to be 3/2. That's my asymptote. Or 1.5. Testing the limit simply means if I get my x value infinitely close, that's the limit, right? If I push the limit and get infinitely close to 1.5, in other words, if I have an x equals 1.50000000001, where would I be? And I will also test right here. What if x was a 1.4999999999999999999, infinitely close to 1.5, but not touching it? Where would I be? Mathematicians don't write that though, okay? We have a simple symbol. Let me show you why. The symbol for testing the limit is this, and you'll see it in calculus. You write the limit of, this is how you say it, the limit of 1/2x minus 3 as x approaches 3/2. Sorry, don't write this yet. As x approaches, you don't have to erase it, 1.500000001. That's how we would write it mathematically. The limit of the function as x approaches 1.5000001. What's the problem with how I wrote this? What do you think the main issue mathematicians will have?
You write 1.501 and then 0.
Like 1.50 repeating 1?
Yeah.
Something like that. Again, even if I did that, what is the problem with that notation? What do you think mathematicians will have an issue with? Possibly, not really, because we can do that. But math just on its own, writing that is annoying. We're lazy. We would rather not write it like that. So what do we do instead? Take a look. We say 3/2, slightly above that. You get it? Slightly above 3/2, or 3/2 coming from the positive side of 3/2. Does that make sense? So how do we resolve this? What you would do is literally plug in a really not close number to 3/2. You can do this. 2 times 1.500001. You could put as many zeros as you want. Okay? As many zeros as your calculator can handle, and tell me what that equals to. Is that a positive number or a negative number? You know that if I do 2 times 3 over 2 minus 3, that is 3 minus 3, and so that gets me 0. Sorry, 1 over 0. Right? And I can't have that. But what if I had a tiny, tiny, tiny amount higher than 1.5? Someone use a calculator. Go. Positive what? Well, positive something. Yeah. Give what did you get in your calculator? Okay, try it. It will be a positive. I want to know. It's good to go through this motion so you'll know why I'm doing this. Yes.
You get negative 2.6 repeating, and then at the end it goes up to 8.9.
It wouldn't be a negative. Try it one more time. Because this would be, if I were to solve this, this would equal 1 over 3.000002 minus 3.
Because you're getting like negative 2.2.
Oh no, I think you, okay, put a bracket over this. You're doing it as if it was BEDMAS, I think.
Okay.
Put a bracket over this.
Okay, I got 5 million.
Yeah, really, really big number. So when x equals 1.500001, I get 5 million. It's really high up there, isn't it? Is it a positive or negative? So what we do is say, essentially, it is basically approaching an infinitely high number, but on the positive side. Make sense? Okay. So using this, we have confirmed on the right side of the asymptote, it's going to be positive. Okay. So far, so good. I'd like you to consider that calculation for the left side. Would you test the limit as x approaches 3 over 2, but from the left side of the asymptote? So what would you put in? Yep. It's not a negative 1.5. It's a number slightly smaller than 1.5, which is 1. Yeah, there you go. You're going to plug in 2 times 1.49999, as many as you're willing to do, minus a 3. What do you get? Some of you who have the conceptual ability or the ability to sort of think about that in your head, you should be able to get the answer right away. Others, just try it. Yes. Yes. You get an absolutely huge number, but on the negative side. So what do I mean by the conceptual idea? You know this number up here, 2 times 1.5001. That's going to be really close to 3. A tiny bit higher than 3. So this number, this denominator after subtracting 3, will be infinitely small. So what is 1 divided by an infinitely small number? Right? It's like I have $1 and I want to group that into 0.0000001 cent or whatever. How many groups do I have? Like it's like that. A big number divided by a small number will be a positive thing. In the same way, a big number divided by a negative small number will give you a negative infinity. All right. So this is how you test the limit. And in doing so, you have confirmed, let's pretend I don't know this. Let's pretend I don't know this. This is how you confirm that from here, I know it's going to be here. And on the left side, I was gonna say it was here, but I know it's a negative infinity. So I know it's gonna be here. I've confirmed it. What else do I have to confirm now based on asymptotes? We've done the vertical, now we test the horizontal. How? How do I test this area? The left and right side of the graph. What am I plugging in? Here we were plugging in an x value slightly bigger than 1.5, slightly smaller than 1.5. How do we test the far side? Yes. 1/3. No, that's you're good at something else. Think abstract, Jake. Yeah. If we want to see what the behavior is all the way over here, choose a really big number. I'm going to choose like 1 billion, basically close to infinity. Okay. Well, this side I want to do a negative 1 billion. How do we write that mathematically? Same idea. Because it's not because we're testing a limit, we write. So for the horizontal asymptote, the limit of 1/2x minus 3 as x approaches positive infinity. So imagine with me. 1/, think of the biggest number you can in your head, and then multiply that by 2, and then subtract it by 3. What do you get? Yes? X arrow infinity. Okay. So it's literally 1/2 times a huge number minus 3. So I'll ask you this. What is 1/2 times infinity? Forget that. Forget. Let's go back. What is 2 times infinity? Infinity. Infinity minus 3 is infinity. So we have 1/infinity, which is very, very close to what? 0. Positive 0 though? On the positive side of 0 or on the negative side of 0? Yeah. As x goes to infinity this way, I have confirmed that it's going to be above the y. Sorry, it's going to approach 0, but on the positive side of 0. Do it again. What is the limit as x approaches negative infinity? 1/2x minus 3. That is again 1/2 times a negative infinity minus a 3. What is 2 times negative infinity? Negative infinity. Negative infinity minus 3 more. It's still a negative infinity. This is 1/a negative infinity, which is basically approaching a 0, but not equal 0. Slightly under, it's going to be on the negative side. It's a minus infinity. So it will be approaching 0, but it'll be slightly under the 0. I'll do it this way. What does that mean? This arrow must connect to this arrow while going through negative 1/3. This arrow must connect to this arrow, and there's no other helpful points for us. But by testing the limit, you can confirm that your graph is that much better. And that's going to be necessary when we do quadratic. How's everyone feeling? So I have 2 suggestions that we can do for the next example. We could do this last example while testing the limit. Or we could try it for something like a quadratic to see why testing the limit is so useful. Who would like to see the second example? With the simpler, okay. And who would like to go to the quadratic to see why testing the limit is useful? Class wins. How about okay, let's do this. You know what? Let me give you some time I want you to try this and see if you can accomplish all of this. Maybe not testing the limit, but try to accomplish everything else in about like 5 minutes. Okay, I'm gonna pause the video and give you an opportunity to try. Okay, if you've done your 5 minutes, I was already doing stuff and I jumped the gun. The first intercept I'm going to do, assuming that you've done domain, is find the y-intercept by plugging in a 0. If you plug in a 0, you get 4 over 5 minus a 0. It's 4 over 5. Long story short, here's my y-intercept. The x-intercept, what is the x value if my function is equal to 0? And lucky for us, that can never be 0. Therefore, no x-intercept. Right? Even that, while I was explaining, that was just a minute, right? A minute and a bit. Asymptotes, let's do it. Using my domain, I already know what my vertical asymptote is. It's x equals 5. And because I'm gonna forget, I'm gonna test the limit right now, right away, right? And then horizontal asymptote, let's pretend I don't know what it is. I'm gonna confirm it by testing the limit. Here we go. Vertical asymptote, what is the limit? So instead of writing LIMIT, mathematicians are too lazy to write even that. So you will see textbooks use the word LIM. Okay? The limit of the function 5 minus x as x approaches 5 from the positive side, so from the right side, what I'm gonna test is 5.000001. So it will be 1 over 5 minus 5.000001, which means my denominator is going to be negative 0.00000001. So that's going to be approximately negative infinity. Question and question. 4? Oh, sorry, 4, you're right. So it would be 4 over a super small number. It's going to be approaching negative infinity. Let's do it again. The limit as x approaches 5 from the negative side, 4 over 5 minus x. That's like 4 over 5 minus 4.99999999999. So that's going to be 4 divided by a positive 0.00001. So it's going to be about a positive infinity. So this is going to help me with my sketch. It's going to be my confirmation. You'll see me use every piece when I draw now. Horizontal asymptote. I don't have enough space. I'm going to do it up here. Horizontal asymptote. I said earlier that let's pretend I haven't confirmed it. Let's figure it out mathematically. What does the function look like or behave as x pushes towards the right side? 4 over 5 minus x. Well, x is going to be infinity. What is 5 minus infinity? Negative infinity. So this is going to come closer and closer to the value of 0. Because it's 4 divided by infinity. But is it going to be a positive or negative? This is going to be 0, but on the negative side of 0. And the limit as x approaches a negative infinity of 4 over 5 minus x. That's going to be 4 over 5 plus an infinity. So it's going to be 4 over infinity. That's going to be close to 0 on the positive side. Woo! Lastly, intervals. No x-intercepts? Great. Vertical asymptotes? 5. Function 4, 5 minus x. 4 is always going to be positive. X will be, let's do a huge number, negative 1 million. That's going to be a positive. And 1 million is going to be negative. Okay, and that's my vertical asymptote. This is curve sketching. Here we go. All right. X can't be a -5 because we have a vertical asymptote there. Sorry, X can't be a 5. Next, I have a y-intercept at 4/5, so somewhere here. Symmetry, I skipped. Asymptote, I did X equals 5, but on the right side, it's going to be a negative, so it's going to be down here. Did I say right side or left side? The left side is going to be a negative. The right side is going to be, what am I saying? On the right side, it will be a negative. So on the right side, it will be a negative. Left of 5 is going to be positive. Maybe I shouldn't even draw the arrows. It's just here and here. Okay. Horizontal asymptote? Yes, there is one. Both sides will approach a 0. So I'm going to draw a horizontal asymptote. If I am going to infinity, it's going to be underneath that asymptote. It's going to be right here. And if I'm going negative, it will be above the asymptote. So connect everything. I need to start on the left side, go through the dot 4/5, and then it has to hit that arrow, and then I teleport to this arrow, and it has to connect to this arrow. Every piece of your calculations are going to play a role in sketching out your graph. If you're doing it right, it will look something like this. Yes. The area you put on this graph, or down here, explain the a couple of things. The interval chart, the sign chart, as well as the calculations we found here, play a role. Sure. Let's start with the vertical asymptote. When it's to the right side of 5, it has to be in the negative y value. So I know it's going to be here. On the left side of 5, it's a positive infinity, so I know it's going to be there. We also tested the horizontal. If I go all the way to the right, I notice that I am approaching a 0, but from the positive side. Sorry, from the negative side, so down here. And if I go way left, it's going to approach 0, but on the positive side, so up here. And then I know there's a 4/5. And do these arrows agree with my intervals? Yes. Left of 5, I am above the x-axis. To the right of 5, I am below the y-axis. Everything matches up. Welcome. Yes, Gwen? Very good connection. You're wondering why. True. If I were to turn this into the format of transformations, it would have to be x first. In other words, it would be 4/-x minus 5. So there is a horizontal reflection, because that's a k value of -1. And 5 here means I move 5 to the right. And look where the asymptote is. it moved 5 to the right. So it does match your AKDC. But we are going one step further because today I want to show you the quadratics. What happens if it can't follow AKDC? Are we stuck? No, we can still use DISAI, whatever the acronym is, DISAI, to graph it. Yes. What a great question. The question was, what's the point of doing that extra work of testing the limit if you already know what the horizontal asymptote is? Which brings us to something like this. Okay. Sometimes you will not have a value of 1 up here. You will see that in chapter 3.3 if you're willing to be patient. Even though you can logically say the horizontal asymptote is 0, I would like you to still go through the motions because that motion will help you solve not so simple. Okay? So I'm going to take the first 5 minutes here to go through this handout, work through just as we did before, and get you to see, hey, is there a similarity in the difference between intervals that are increasing, decreasing? And then we'll find the end behaviors. I'm going to skip this because I already sort of taught you just now. I don't have to worry about this. I just want you to see a parallel between this and its reciprocal, just like 3.1. And then we're going to go straight into sketching because that's going to be your weekend homework. I need to get through this so that you have this for homework. And for everyone else who's not here, sucks to be there. Okay? Not that I don't want to encourage the awards assembly, but we gotta move. I need to get this through before the long weekend. All right. The 2 things that I want to mention as very, very special is that just like before, the zeros of a polynomial will become the vertical asymptotes of its reciprocal. And also, although the intervals where the function is positive and negative are still the same, just like before, the areas where it's increasing or decreasing will switch, just like our regular interval. Okay? This will help us. So what are the zeros? If I said that this function was equal to a 0, what are my x values? Positive 5 and negative 3. On the flip side, what are the values that will make the denominator a 0? In other words, what are my vertical asymptotes? X equals 5 and negative 3. They are going to always coincide, always correspond. Couple things once again, if I were to draw this as so the domain x cannot, x just belongs to real numbers. For here, x does belong to real numbers, but x can't equal a 5 or a negative 3. If I were to draw this, I'm going to skip the drawing because we have to learn to sketch. Keep this in mind. Maybe if we have time, I'll come back to it and fill it up. But you will see that the intervals for a parabola, it goes down up to a certain point to the vertex, and then it goes back up. So here, it is decreasing and it is increasing. When you have a reciprocal function, you will see that these points become vertical asymptotes, and it starts doing some funky stuff. Okay, it's because I don't have time and I can't explore it the way I want to. It's unfortunate. Let's jump. Notice how my list is significantly shorter. I took away all the parts that are calculus based. Let's sketch it. All right. I noticed that on your sheets, the plus 36 is missing. Would you please add it down? Please add it in. I don't know what happened, but the plus 36 is missing. Do we add it in? Yeah. When it's given to you as a polynomial, that doesn't help us sketch. So here's where your factoring once again comes in. We need x minus 6, and of course, x minus 6. There we go. What is the domain? Okay. Please notice that they are the same, so there's only one restriction. And that also becomes my vertical asymptote. Okay. Would you please try this? I'm going to ask you to find your x-intercepts, find your y-intercepts, and see if you can identify the behavior of the asymptotes. I'm going to pause the video. I'm going to give you, once again, 5 minutes. That was just about 5 minutes. Here we go. So if I were to do this again, because I've done this, I don't know how many times, I'm going to do the easy one first. My y-intercept is when x equals 0, which is -4 over -6 times -6. This is positive 36. In other words, my y-intercept is 0, 1 over 9. X-intercept is when 0 is the y value, and I need to make this fraction into a 0, which will never happen. No x-intercept. All right. Symmetry, I am going to skip. Asymptotes. Okay, so the asymptotes, as you know, it just got really big, right? For the asymptotes, vertical asymptote we have confirmed is equal to a 6. So let's test the limit. What does it look like if it's just above 6? If it's just above 6, I have an infinitely small number. Maybe this will help. Does that work? If I write that, does that make you laugh and get you to memorize it? Okay, it's really, really small. And so if you square it, it gets smaller. Here's my argument. 0.1 squared becomes 0.01. It gets smaller. So if you have that, it will be -4 over a really small number. The final answer is going to be essentially negative infinity. Yes. Yeah, it will be 6.00000001 minus a 6, which leaves you with 0.00000001 in here. So it's really small. So when I square it, it becomes smaller. I'm going to test the other limit. As x approaches 6 minus, sorry, it's not 6 minus, but 6 from the smaller side, so 5.9999999. So 6 point, let's say 0.00001, whatever. Again, it's going to be a positive small number squared. That's going to be, again, negative infinity. You're looking at me confused. What's up? Oh, you know what? That's a good catch. If I have 5.99999, you're right. This is a negative small number, but I square it. So it becomes a positive. That's a good catch. Okay. So it's let's talk about horizontal asymptotes now. I don't know what the horizontal asymptote, I do know what it is, but let's pretend I don't know. horizontal asymptote, I am going to test the limit of this function as I approach infinity. So infinity minus 6, it's still infinity. So in the numerator, it's infinity squared, which doesn't change anything. We are going to approach 0, but from the positive side or the negative. It's going to be a -0. I know that sounds weird, but it's going to be slightly under 0 is what I'm trying to say. Limit. As I go towards the left side, same thing. I have a negative infinity minus a 6, and that is squared. Well, negative infinity minus anything, it's still negative infinity squared. That'll be a positive infinity. -4 over a positive infinity is 0, but on the positive side or the negative side? It's the negative side. -1 million times a -1 million is a positive number in the denominator. So it's -4 over a positive. So you get 0 on the negative side. Yes. This one? It's because if the denominator is a negative, so the negative is small number, right? It's squared. So the denominator will always be a positive. It's -4. Okay, these are good questions. Any others? Yep.
What's X? What's C? Whatever it's X goes to positive.
No, it won't. This calculation told us it is for this particular one. So we have to do this every single time, no matter what. Okay. For what it's worth, I'm recording. So if you ever want to sort of, yeah. But it's the same topic. We're doing the same thing. This part is the only part that's new, and it's just one concept. It's very doable, and no one needs to panic. Let's do this. Now that we have confirmed and got so much detail around the asymptotes, let's finish off the intervals. What are my x-intercepts? None. What are my vertical asymptotes? 6. So I have a -4 on top. I have x minus 6 squared. Well, that's nice. I don't have to do any calculations. Why? Because -4 is always negative. And anything squared is always positive. So both left and right side of my vertical asymptote, I will be underneath the x-axis. Does that make sense here? Yes, both sides are underneath. Now we're going to put all of this information together by graphing. Here we go. Domain. Well, yeah, domain is domain. I know it can't be a negative, it can't be a +6. Good. Y-intercept, -1/9. So something here. Vertical asymptote, 6. To the left, to the right of the asymptote, it's a negative, so it's going to be somewhere here. To the left of the asymptote, it's going to be negative, so it's going to be somewhere here. Horizontal asymptotes. As I go to the right, I am approaching 0 from the bottom side. So it's going to be here somewhere. As I go to the left, it's approaching 0 from the bottom side. So it's going to be here somewhere. Yes, yes. Go for it. And lastly, the charts agree that if I'm to the left of 6, it's going to be underneath the x-axis. If it's the right of 6, I'm going to be underneath the x-axis. So connecting these bars together, connecting the dot together, connecting the charts together. There's my graph. All the pieces are coming together. So everyone, there are plenty of other examples. Oh, there's space there. There are plenty of other examples that you can do. You have 7 minutes before the bell rings. I would like to challenge you and see if you can graph this on your own before you go. I will factor this for you because I will. See if you can perform everything here, including testing limits, and sketch the graph accurately. I will have the answer key of this all filled in and posted on Brightspace so you can confirm over the weekend. Come Tuesday, since it's a long weekend, come Tuesday, as I promised, I'm gonna have a sweater on that has a math joke, but it involves a graph, and we're gonna use that sweater to see if you can figure out what the graph is, based on your knowledge of sketching. It's all in the effort of a sketching quiz coming up on Thursday. It's yesterday and today, all that stuff put together. You just gotta practice, practice, practice sketching. You will be over. Yes. Anytime from now on that I ask you to sketch, typically it'll be too complicated to use factoring, like remainder theorem and factor theorem, right? It's not impossible, but that won't be enough. So something like this, like a reciprocal, go through all of it. I think this quiz is off. I don't remember. I'll let you know next week. Don't do it for now. Yeah. This is more useful for calculus. As of right now, I don't think you have to test symmetry. By calculus, I mean like next semester if you take calculus. I'll let you know if this becomes useful later on, but right now, it's not clearly, as you can see, it's not important. Yes. Essentially. Again, I'll have to confirm with you. But the main portion is, do you understand each piece? Do you know how to figure out the restriction, the vertical asymptote? How do you know what the horizontal asymptote is? Limit, blah, blah, blah. Okay. Yeah. Everyone, essentially, the rest of this sheet, I know I only did one example with you, but as you can see, all the steps are the same. See if you can do the other 3 on this little package I gave you. There are, I think, textbook questions you can do as well on the very bottom. Yeah, but it's all sketching. See if you could pull that off. That will be your weekend homework. If you can do that and you're like, I actually get this, do some random function on your own. You're like, yeah, I can sketch that. That's a great place to be. See if you can complete all of these steps anywhere between 5 to 10 minutes. That's your goal for this weekend. Any question you get from the text, see if you could sketch in about 5 to 10 minutes. Yeah, that's a good place to be. Any questions? Okay.